Hello everyone, this is Vikram and welcome to my channel. In this video, we are going to talk about one of the important topics in Kubernetes, that is Kubernetes stateful sets. We are going to understand the difference between a stateful application and stateless application and why we need stateful set controller for deploying stateful applications such as databases. We'll also understand the difference between a stateful set controller and deployment controller and why Kubernetes have two different controllers for deploying applications. And we often come across this term called headless service while we use stateful sets. You'll understand the need for headless services when we have cluster IP services and the differences between them. We'll be deploying MySQL database inside the Kubernetes cluster using Helm charts and learn about some of the storage concepts such as persistent volume claims and storage classes. For all the topics that we are going to cover in this video, that is the deployment, stateful sets, headless and cluster IP services, we're going to see some demos using MySQL and other applications as well. And as a major application, we are going to see a simple to-do application written in Python that gets connected to a MySQL database as the backend database. So we'll have some to-do entries from the UI and these entries will get stored in the MySQL database. So we are going to see how to deploy this MySQL database as a deployment and also as a stateful set, and we'll see the differences between them. So these are the various topics that we are going to cover. We are going to talk about how a pod can talk to another pod, that is pod to pod communication. We'll see the differences, like we'll see the challenges that we come across when we directly talk from one pod to another pod. We'll also understand the pod DNS entries, that is A records and AAA records. We'll see the differences between the headless service and cluster IP service and why headless service is needed when we talk about deploying stateful applications with the stateful set controller. We'll also see the need for data replication when we talk about deploying multiple instances of a database in the Kubernetes cluster. So we'll see how to write a simple data to a single GB instance with the help of headless service. At the same time, read the data from all the available instances of a database using the cluster IP service. We'll also see some basic concepts such as storage classes PV and PVCs while deploying MySQL database using the Helm charts. So if you're planning to deploy a database or any stateful application in the Kubernetes cluster, then knowing about stateful set controller and a headless service is very important, because these are the mandated things that we should know when we try to deploy databases as well as manage them inside Kubernetes environment. This is the to-do application that we are going to see in this demo. This application is written in Python and database as MySQL. All we have to do is write some to-do items here in the box and click on add button. This gets directly written into the MySQL database. Now, while deploying MySQL database, we'll see how to deploy it as a deployment controller. With the deployment controller, at the same time with the stateful set controller, and we'll understand the differences and why we prefer stateful set controller when we deploy databases. So before understanding any of these concepts, let's understand how pod-to-pod communication usually works. Let's assume I have two different pods. First, we are considering without the need for services. So I have one pod which is a Python based application and the other pod which is MySQL database. Now I want this Python application to write some data into the MySQL database and also the ability to read the data from MySQL database. So how do I first connect to the MySQL database from my Python application? So usually there are two ways. So one is a simple DNS name and the second one is the IP address. So we'll understand whether these two are really possible in case of pod-to-pod communication. Let's assume I am using the IP addresses when I'm talking across the pods. Let's say pod A uses the pod B's IP address as a way of connecting to the pod B. So let's assume I have the IP address which is 172.17.0.4. The pod A uses this IP address of pod B, whatever is the service port. Here the service port in the sense not the Kubernetes service but the actual application port that your application is listening on. Let's say if it is Postgres database, I see it is 5432. So something like this. So should I use IP address directly? I cannot use the IP address directly because of one possible reason, that is the pods in Kubernetes environment are ephemeral in nature. That means if the pod dies due to any issue and if any new pod replaces it, so the IP address of the pod usually changes. That means the pod along with their IP addresses are not stable or static in case of Kubernetes environment. So if it is a simple pod, if it is killed, it won't come up. But if it is managed by any deployment controller or replica set or replication controller, it usually comes up, but it will come up with a different IP address. So communication through IP address is usually not possible. Of course, if the pod is still running, it is possible to get the IP address and talk to it, but usually the IP addresses are not preferred way. And the next way is the DNS name. So what if I use the pod name as the identifier? That means I'll simply use HTTP colon the name of the pod. So let's assume the name of the pod that I've set as pod_b, and whatever is the container port being used in your application in pod b. So let's assume this is the just an HTTP call. So can I just use the name of the pod in this case? It's not even possible, because DNS resolution with just the pod names is not possible in case of Kubernetes. So in case of service names, it is possible. That is, if you have a cluster IP service, that will be resolved to the cluster IP. So the name of the cluster IP service resolves to the cluster IP itself. But in case of pods, it is not possible. That means I cannot directly use the pod name as the identifier. So this is not possible. That is, with the IP address is not possible, with the name of the pod is also not possible. And let's assume you need a simple DNS entry that a pod A can use to talk to pod B. So Kubernetes supports DNS resolution in this form, where you have the pod IP address dot namespace in which it is deployed, and pod cluster domain dot example. So which means if I have to get the DNS entry or the simple FQDN for this pod, it is usually the pod IP and the namespace pod.clusterDomain example. In case of pod A, since its IP address is this, so I can have the IP address in the default namespace pod.cluster.local. So cluster.local is the default domain. And if you see this IP part, so IP doesn't have any dots over here. So here these octets are separated by hyphen. So which means the entire FQDN is dependent on the IP address. So I cannot also use the fully qualified domain name of a pod, because it is dependent on the IP address of the pod, which is not stable. So the same thing, if pod A wants to talk to pod B, all it has to do is use this FQDN of pod B, which is the IP address of the pod B, and every octet is separated by hyphen dot the namespace in which pod B is listening on, it is deployed, and pod.cluster.local. Since this IP will change if pod B restarts due to any reason, this is not at all the recommended way. And also, why I can't use the IP addresses directly is, let's assume the database or second microservice. I'm assuming this is one microservice and this is another microservice B, in which there are 3 replicas of microservice B. And for each replica, I get a unique name like this. So we'll talk about how these unique names are generated, and also the unique IP addresses within the cluster. Now let's assume I want pod A, which is microservice A, to talk to microservice B. Since I wanted to load balance all the requests across all the instances in microservice B, so I have 3 different replicas just to share the load. Now this pod A has to talk to any of these in a load balancing way, which means if pod A talks to this instance for the first time, second time it has to send to the next available instance, followed by the third available instance, thus load balancing the request. So what are my challenges in this case? The first challenge is the pod A should know the available IP addresses assigned to all the instances of microservice B. That is the first challenge, because I need to maintain those records and I need to send the request in a load balancing fashion. The second thing is, once if I have the IP addresses available in pod A or microservice A, so it can talk. But if any of the replicas of this deployment B is down, and if it is replaced by another new pod, its IP address usually changes. That means that information has to be given to pod A, because pod A is load balancing the request. That means it is sending the request in a load balancing way. So if the IP changes here, it has to be updated. So how do I update pod A with this latest information? So if the pod is in a running state, I cannot update, because I can give that information in 2 ways. One is through environment variables, or else I can also give it as a config file in the form of config maps or secrets. So in all these ways, I need to bring down the pod A first, give its latest information about all these IP addresses, then only pod A can take into consideration. In case if this IP address changes due to any reason, that information has to be given to pod A, which means so pod A is highly dependent on the IP addresses within your cluster. So this is also not the correct way. Now what will happen if I use some sort of abstraction in form of services? So let's say pod A wants to talk to pod B. So as I said, pod A cannot use the name of pod B as well as the IP address of pod B because both of them will always change. So I created this abstraction in the form of service. So here services are nothing but it's just a configuration that lies within your Kubernetes cluster, and it is not always running component like your pods, which means there are zero chances of this being down, because since this is a configuration, unless you delete this configuration will reside in your cluster forever. But in case of pod, if it is dead due to some issue, it may be in the stopped state, or it may be replaced by a new pod depending upon the controller which is being managed with this pod is being managed by. But in case of service, these are just the configuration rules. But why I need services in the first place? So here services act just like a proxy, where I can forward the request to the service, and service will take that request and exactly forward it to all the backend pods it is managing. So we all know the concepts of labels and selectors, where if I have to create a service for this pod B, I can use the labels that are given to this pod as the selector for this service. Then this service will automatically forward the traffic to this backend pod whenever it receives the request. But how does it receive the request, and how does this DNS resolution actually works? So whatever we are saying here is pod A talks to service, and service forwards the request to pod B. So which identity this pod A uses to talk to this service? It uses the service name. So here in this in the internal HTTP call, all it does is it will use the name of the service. Let's assume I gave the name of the service is svc_p. So it uses the service name followed by the namespace. So the namespace is a default, let's assume, because this service is deployed in the default namespace. But if your both pod and services are in the same namespace, you don't have to give dot namespace. So this is the API call, the HTTP call. So you can also use the fully qualified domain name of the service, which is svc.cluster.local. So this is the API call that I'll use to talk to this service. And in fact, service has an internal port, the incoming port, which we call it as port, and the outgoing port, which we also call as target port. So this target port usually matches the incoming port of the container or the container's port. So here when I create the service, I should also give it the incoming port and the target port. So incoming port, if it is 80, I don't have to put :80. But if the incoming port is 8080, since your pod is talking to this service, so I have to give the name of the service, which is FQDN, colon the incoming port, which is 8080. So whenever the service receives this particular traffic on port 8080, since in the service configuration I mentioned the target port as 9090, so when it receives the request, it automatically forwards the request to 9090 on this particular pod. So this is the kind of abstraction. But how does this act like an abstraction? So here services are tagged to pods. If the pod is replaced with a newer pod, let's say the old pod got deleted and it is replaced by new pod, but this new pod also comes with the same labels which are set in the pod manifest files. Since this service is using the pod labels as a selector, so whatever pods that available in the cluster with the same label will be managed by this service, which means service here just uses the labels as the identifier to identify a set of pods. Here it is not taking care of the name of the pod or the IP address of the pod, it is labels and selectors. That means if this pod is if it is killed due to any reason, and if it is replaced with a newer pod, it always comes under the load balancing of your service, which means all I have to do is I have to talk to the service will forward the traffic to the backend pod. So this is how we create an abstraction. But how does this resolution actually works? So if I use the name of the service directly, like from pod A, I'm using the name of the service, which is svc_b dot the namespace, and the fully qualified domain name like svc.cluster.local colon the incoming port. Let's assume the incoming port is 80. So if I simply use this fqdn, will it resolve? Actually yes, it will resolve, but to which IP it will resolve? So this one will be actually resolved to the IP address of the cluster IP service, which means if I use the name of this service like svc_b colon the actual port, which is 80 in this case. So this svc_b should be actually resolved to the IP address of the cluster IP service, because we know that every cluster IP service gets an internal cluster IP. So this will be resolved to the cluster IP and the port, which we already hard coded to 80. But from where this resolution is happening? So how come this name is getting resolved to the IP address of the actual service? So whenever the pod A uses this as the HTTP call, first this one will be resolved to the actual IP address by querying the core DNS service, which is responsible for the DNS resolution within your Kubernetes environment. So this core DNS runs in the kube system namespace, and through a kube DNS service which is running the same kube system namespace, we can access this core DNS. So here the core DNS will actually can be deployed as a deployment, or it can also be a daemon set. And in order to access this deployment, we create a service inside the same kube system namespace. Now, so this DNS resolution, that means this is acting like the IP. Through this IP you can access core DNS, which means this IP is nothing but the DNS resolver's IP. So this IP address will be added to all the pods that you create in the cluster under etc_resolve.conf. So in any case, if you use the name of the service, so that will be resolved by sending that request to your kube DNS service and turn forwarding that to the core DNS. So the name of this kube DNS service will be entered as the static IP address under this configuration. So if you create any pod and if you go to this location, you'll always see the IP address of the kube DNS service under the kube system namespace. And since this will be resolved to the actual IP address, and since this IP address is corresponding to the cluster IP, so this request will come to this cluster IP service. And since cluster IP service knows where to forward the traffic due to labels and selectors, so your request will ultimately raise the backend pods. So this is the first way. In other cases, like in case if the other set of microservice, like the microservice B is deployed as the deployment controller with multiple replicas like 1, 2, and 3. So this service will also act like a load balancer. Here, this pod A, in case if this is not available. So what we discussed is, in case if your services are not available, this pod A should know the IP addresses of the backend pods, and it has to load balance the request manually. So what if I put this service in this case? In case if I put this service, this pod A will always talk to this service, and service will know how to forward the traffic in the round robin fashion. In this case, so these are the labels, which are the same labels for all the pods, and the same labels I'm using as a selector. That means this service is managing these 3 pods. So if anything comes to this service, it will automatically forward it to all these pods in the round robin fashion. Here this service is using labels as the selectors. It is not considering the IP address on the individual pods or the name of the instances in this deployment. Here it is just taking care of the labels. So it always scans the cluster for all the labels on the pods. So let's say that if app::db is the label that I set to all the pods in this deployment, and the same label I'm using as a selector for this service. Now what this service will do is, service will scan the Kubernetes cluster for all the pods with this label, and then it will bring under this load balancing algorithm. So here this service will act as a load balancer, because any request comes onto this service will always be load balanced if there are multiple instances of your application that are being managed by this service. So now here I created an abstraction, so I don't have to directly talk to the backend pods. I'll directly talk to this service using its service name, and if there are multiple instances, service will automatically load balance the request. So my issues are resolved with using services. So that is the uses of your services. But consider the stateful applications like databases. So what are the various challenges I usually face? So in case of stateful application, so let's assume I'm using database as the stateful application, and this is one my Python pod. Okay, so this is my actual front-end application written in Python, and I need to connect to the database. So for deploying the database, I used a deployment controller, and there are 3 replicas here. So 1, 2 and 3. So now I exposed my Python application through a load balancer service or node port service, using which my users can access the front-end application. So here I'm taking this as a front-end application. Now let's say I have a user who is just signing up for this particular application. So what he'll do, he'll fill up the sign up page, and then he'll click on sign up. So usually that request through the front end has to send to the backend to store the data. Here the backend is MySQL database, so the user data has to be stored in database. Now what we said is, in case of cluster IP service, any request that comes to the cluster IP service will be load balanced. That means if one request comes here, that request may redirect it to this instance. Second time the instance, the service might redirect the request to this instance. Third time the service might redirect the request to this instance. So this is not always a stable one. It is always round robin. So what if I create the if I sign up for this particular application and the request went to this particular instance? So this is where my sign up data is stored. Sign up data in the sense my username and password data stored in the last instance here. Let's assume. Now the second scenario where the user who signed up for the application is trying to log in by entering his username and password, and he will try to click on the login button. Let's assume. Now the request went to the front end. Through the front end, it has to go to the back end to see whether the actual user data is available to allow him to log in into our application. Okay, so he entered the username and password. So it is just like a read request. So his request came to the cluster IP service because the pod A sends the request to all the backends to this service. Now service, since it load balancer request, let's assume it is sending the request to the second instance. So in this case, my login will be unsuccessful because first time when I created my account, the data got stored in this third instance. But when I'm reading, your service forwarded the request to this instance where the login data is not at all available. It is available here. So this is the disadvantage of using cluster IP service with stateful applications, because here I have a state here, but that state is not maintained here and here, because I created the user data here which is not available here and here, which means if my requests are not properly redirected to a particular instance where data is available, my my request will be unsuccessful. But in case if you have only one instance of database, and if this one instance takes all the write and read operations just like this is okay, because the same instance is taking the write request and the same instance is taking the read request. So your data is here, you're writing it here and you're reading it here. But usually we will not just deploy one instance of database or one instance of a single microservice. So this is not the actual use case. So let's understand the use of headless services in this case, because using cluster IP service will send the request in a load balancing way. Let's see what is the use case of using headless service. The first thing about the normal cluster IP service is the cluster IP service will be resolved to the cluster IP, and whatever the request that cluster IP usually gets, it will always load balances the request. Here the pod A is directly talking to the cluster IP. Here backend instances identity are completely hidden. You have no way of directly talking to the backend instances. But in case of my database applications, I would require one single thing here. Here I want this pod A to write to a single instance and probably read from the same instance. So which means I cannot directly go through the cluster IP, because going through the cluster IP will always load balance the request. That means the requests are randomly load balanced. So I wanted to just bypass this service. So what will I do in this case? So here I'll use headless service. In case of our normal service, we know that the DNS query, that means if we DNS query the service name, Kubernetes will always return the IP address of the service. I'm going to prove everything in the demo. So Kubernetes will always return the IPs of the service itself. So here if I do ns lookup from within this pod A, ns lookup of this particular cluster IP service name, it will always return the IP address of the service but not all the backend instances, which means I have no way of getting to know the IP address of my actual pods. But in case of headless service doesn't need any cluster IP, because here we are directly trying to talk to the pods. So in this case I should not get the cluster IP when I DNS look up the cluster IP service name. So in case of headless service, what I'll do is I'll simply put the cluster IP to none. That means I'm asking Kubernetes not to assign any IP to this cluster IP service name, because I want to directly talk to the backend pods. So here I want this pod A to directly get the IPs of the individual pods, so that I can just talk to the particular pod using its IP address instead of proxying the request through service. So if I just go to the cluster IP service, all I get is the IP of the service but not the IP of the pods. But in case if I use the headless service, I'm going to get the IPs of all the backend pods that this headless service is managing. So in this case, I'm getting the IP address of individual pods dynamically, so that I can target a single pod. Let's say if I have 3 instances and I always want to read and write from the second instance, since through headless service I will get that IP address of the backend pods, it is easier for me to target them. So in what all scenarios we are going to use headless services? So in this we use headless services for pod to pod communication, because here in case of cluster IP service, you talk to the cluster IP and cluster IP will forward the request to the backend pods. But in case of headless, you are directly getting the IP address of the backend pods. So pod A can directly talk to any of the instances of pod B. I mean any of the instances of microservice B. And also in case if you want to deploy stateful applications such as databases, I can use headless service, but we are going to talk about those master slave configuration and stateful applications in some time. So I have here a simple YAML file where I have a deployment, and this deployment is having 3 replicas, and there are some labels on individual pods here, and I'm using these labels as selectors for the deployment, so that deployment will try to manage 3 replicas all the time in your cluster. And the container port of the Flask application is 5000. So this is a simple deployment of 3 replicas. Now if I create a headless service for this 3 instance of the Flask application, all I have to do is I have to set the cluster IP to none, because this is a headless service. So in case if I'm setting this cluster IP to none, it becomes headless service. But if I don't put this entry over here, it becomes a cluster IP service. So that is the difference. So with none, it becomes a headless service. Now as a selector for this service, I'll use the same labels on individual pods, and the incoming port of this headless service is 80, target port is 5000, which should actually match the container port of your application. So this is how the headless service. But here let's say these are the backend pods, and I've created a test pod like Nginx or any dumping pod. So in case if I talk to this headless service from other pods, so what I'm going to get is not the IP address of the headless service. Instead, I'm going to get the direct pod IP address to Nginx. So which means my Nginx can talk to individual pods, since I'm dynamically fetching the IP address of the pods. In case if this headless service is replaced by cluster IP, and if there is any pod, which you call it as client or anything like that, so if it is talking to that cluster IP service, all it is going to get the cluster IP only. Since I'll get only cluster IP, I cannot target the individual pods, because that information is not there with my Nginx pod. And anything that your cluster IP receives, it is always going to load balance. But in case of headless service, there is one concept or misconception here, is that if I talk to headless service, so many will think that it won't load balance. It's absolutely wrong. That means if through any pod, if you are talking to the headless service, it will still load balance the request just like your cluster IP service. But in this case, it is called DNS round robin, which I'm going to get in some time. The only advantage that I'm going to get with headless service is I will get the individual IP addresses. At the same time, if I'm sending the request to the headless service, I'm also getting the load balancing, but this time this is called DNS round robin load balancing, because here whatever is the name of the headless service that use, it is representing all the pods here. That name is not resolving to the IP of the headless service, just like your cluster IP. In fact, this headless service is forwarding, is just like acting like a single DNS name for all the backend pods. This is why it is called DNS round robin, where a simple DNS call to the headless service name will result in multiple results. This is DNS round robin. So in case if you apply this manifest file, all you are going to get is cluster IP as none. And here, if you see, I'm just creating a temporary pod, and I'm just using NS lookup to DNS lookup on the name of the headless service, which is headless flask. Here, instead of getting the IP address of the headless service, here I am getting the individual pod IPs. Since I am getting the individual pod IPs, I can directly talk to individual pods. But in case if this is a cluster IP service, if I use NS lookup, I am going to get only single IP address, which is the cluster IP's IP address. That's the difference. So now since I'm getting the individual pod IPs, all I can do is I can just target the individual pod and the container port, which means I'm able to now connect to individual pods. Okay, so now I can talk to any of the pods. So with headless service, what I can do is, so if this pod wants to always talk to this particular replica of this deployment, all it can do is it can just use the so first question is, as I already said, will this headless service always forward the request to the first pod? It's not correct. This headless service, even if it is cluster IP service, whenever it receives the request, it will always try to load balance. Here, even though this is cluster IP or headless, any request that those services receives will always be load balanced, which means if I get a write request to this pod, and if this pod is using the headless service name or cluster IP service name, this will still load balance. So you will not be sure whether this write request is landing or getting redirected to the first instance or the last instance, because these services will always load balance. And the same thing will work with cluster IP service. But in this case, then what is the advantage of using headless service in this case? That's the question. So cluster IP is also load balancing the request, headless service is also load balancing the request. Then what is the advantage? So the advantage here is, say in case if I use curl request within this pod A, so all I'm doing is I'm using the curl request with the name of the service colon the container port. Here, why I'm using the container port, why not the incoming port of this headless service is, here whatever the request that your headless service is getting, it is directly forwarding it to the backend ports. But since it is still load balancing, I'm directly using the headless service name colon port number. But here this headless service name will not resolve to the first instance of your pod. Okay, so it will be load balance. That means every time when you make a new DNS query to that headless service name, it is going to result in a different IP address, which are the IP address of the pod. So which means your headless service is still load balancing, but in this case this is called DNS round robin load balancing, because a single DNS name is giving the different IP addresses. But what is the need of headless service in this case? So headless services are to be definitely used with stateful sets to provide unique identity to each pod managed by that stateful set. So each pod gets a stable DNS name, and these DNS name will be persistent across your pod restarts. So we'll understand them in bit. But before understanding the stateful applications, let's also understand the difference between stateless and stateful applications. So the difference between the stateless and stateful applications are, so stateless application doesn't depend upon the state. So your application doesn't save you the client data for the subsequent sessions. These are true in case of web servers like Nginx, Apache or Node.js, where every time when the client sends the data to the application, so this request will be a completely fresh request. Here the client data, that means from which browser he is accessing, from which location he is accessing, doesn't have to be stored within your application. And in case of your Nginx, so your Nginx application, let's assume it always serves the static HTML pages. So these HTML pages are static, these are not dynamic information. That means any user, when he accesses that HTML application, he is going to get the same output as every other user. In case if I increase the number of instances of this stateless application from 1 to 5, still every user is going to get the same response, because all these 5 applications are basically serving the same static responses. So you can simply scale a stateless application by deploying it on multiple servers. They can scale beautifully and horizontally, and these are much faster because they don't need any external storages, because so these data are not important, because these data are within your container or pod itself. So if the pod is killed and if any new pod replaces it, still the application within that pod will serve the same responses. But in case of stateful application, they depend upon the status, the state of your application. That means they save the client data and use them in the subsequent request, which means if I log in, if I sign up for a website, so that website has to store my user data. So next time when I try to log in, so they have to accept my login credentials, which means the data has to be stored for subsequent users. And all modern applications usually connects to a stateful application like the databases. So in case if I use Node.js as a front-end application for us for a simple shopping application, so that shopping application has to store your user data for subsequent login requests. So these are all called stateful application. And also a stateful application needs a persistent store to store its state and read data, which means let's assume this is a database, and I cannot simply store all the database within the containers file system or within the pods file system, because if once the container or pod is killed, the data within them gets lost. So that's the reason why the data which these applications are holding has to be stored somewhere outside the actual container or pod, because if the pod gets deleted or gets destroyed due to any reason, I still have the data in my backup, so that next time when I create the same application, they can read the data from the backup. So this is how we deploy stateless and stateful application. So in case of stateless application, we use cluster IP service. In case of cluster IP, whenever there is a request from the client, so it can be randomly load balanced and it can be sent to all the backend instances like this, because so these 3 instances are serving the same data, which means even if one responds with the information, or if 2 responds with the information, 3 responds with the information, they are still going to respond with the same data. But in case of stateful application, the states are important. So if I take these are the databases, and if someone writes any data to this database, let's say I created a login, I signed up for a website and that sign up data is here. So the next time when the same user tries to log in, the read request should also get redirected to this request, to this instance, because this instance is storing or holding your sign up data. But in case if the write request goes to this instance and the read request go to this instance, your user will not be able to log in, because these are all inconsistent read and write operations. So we'll understand how to replicate the data in some time through stateful sets. Now let's understand stateful sets, why stateful sets are needed in the first place when we have the deployment controller. So a stateful set in Kubernetes controller used to run stateful applications like your pods in the Kubernetes cluster, and they'll always manage the desired and current state. Let's say if I need 5 replicas of my application, so stateful set controller makes sure that the 5 replicas are always running within your Kubernetes environment. If any of the instance goes down due to some issue, the Kubernetes will create one more instance to balance the desired and the current state. However, the same is being done by your replica set, replication controller, and deployment. They are also managing the total state or the total number of replicas running in with your Kubernetes environment. So if these controllers are already managing the same thing, why we have a different controller called stateful set controller, and how this is different from your deployment controller when we try to deploy databases or any stateful applications. The first thing that sets stateful set controller apart from your deployment is data replication. So we'll understand what is this data replication and why this is needed in case of stateful applications. So let's assume I have created a simple to-do application that is basically storing your to-do list here to MySQL database. So I've used a deployment controller, and that too with only one replica of my MySQL database running. So I have this pod A which is serving my front end, and this is exposed as load balancer or node port service so that the users can access it. Now let's assume a first user, he created an account. Now the request will go to the backend, because this pod A, which is my front end, will call the backend MySQL database to write the data. Since it cannot directly talk to another pod, so I've created an abstraction in the form of service, where this pod A will talk to this service, and service will forward the request to any of the backend instances. So in this case, I only have one. So this service will simply proxy the request. So I'll use this name like HTTP call with the name of the service and the incoming port. So that is the port. So this request will go to the service, and service will automatically forward it to the database. Okay, so let's say I have only one instance. Now all the write operations, all the read operations, or any delete, whatever it is, it will always go to the single instance, which means I'll get consistent read and write calls, because write and read operations are always getting targeted to a single instance. So if I create a sign up, if I sign up for that data, my data is here. If I try to log in with that details which I used, my requests are getting redirected to the same instance. So I'll be able to log in. So what if I increase the number of replicas to 3? So if I increase the replicas to 3, we all know that. So if the write request go to this first instance, and if the read request gets redirected to the third instance, I'll not be able to perform anything, because the data is here, but I'm searching it here, which is practically not possible. So deploying stateful applications like your MySQL databases through the deployment controller, it's not possible. Now what are my available options? So the reason why I'm not able to read the data from all the instances is I don't have the data replication. So here, whenever I write the data to the first instance, so I want my other instances to replicate the data. So which means if I write x is equal to 1 in first instance, I want all the instances to replicate the same data, which means if I create a user, and if that data is stored here, I want the data to get replicated here. So which means if the user tries to log in, that request can be redirected to the any of the available backend instances, because all the backend instances have the same data. So my login will be usually success. But in this case, how do I replicate the data? So in what method I will replicate the data? What are the available options? So we are saying we'll write it to only one instance, that is here, and the other instance should be able to replicate the data, so that the read operations can be any of the instances. So if I have 3 replicas, I can read from all the replicas. But how do I create this replication? What algorithm I'll use? So Kubernetes also has a beautiful documentation for this replication algorithm, which we are going to see now. But let's see what are my various options and how can I just replicate the data. Let's assume I used MySQL, I deployed MySQL through a deployment controller. So we all know that deployment has a name. So let's say I've used MySQL as the name of the deployment, and every replica. So if I consider replicas as 3, so every replica gets a unique name. So it is a combination of the name of the deployment and a hash value that is generated by the replica set, because every deployment creates a replica set, and the pod hash. So this is the name actually. So you'll have the deployment name, the replica set hash, as well as the pod hash. So let's assume these are the different identifiers that are created for each pod. If any of the replicas goes down due to some issue, Kubernetes or the deployment controller will replace it, but this time it will get a new identity. So new identity here in the form of the pod hash. So here this is the deployment name, this is the replica set hash, and this is the pod hash. So if the pod is replaced, the hash will change. If you create an upgrade to the existing deployment, that existing deployment will create a new replica set. In this case, your replica set hash will change. So this is how the names in the deployment will change. Now that we know that the name of the pods will change if they are redeployed or if they are upgraded. Now how do I replicate the data in this case? Let's say these are the names of the pods. Okay, so now I need to create a replication. So how do I create? The first thing is I can use the IP address of the master pod. So I'm taking this as the pod 1. So where all the read requests are where all the write requests are redirected. Let's assume I wrote into this instance. Now what I'll do is I'll ask these 2 and 3 replicas to always use this IP address of the first pod to replicate. Okay, so your 2 and 3 talks to this IP address within the cluster, and then let's say that they replicated the data. That is fine. So the replication is established. So what if the IP address of the pod got changed because this instance due to some issue it got restarted, that is the pod restarted, the IP address changed. So when the IP address is changed, the information has to be provided to the other instances because they should know the correct IP address. So how do I supply the IP address in this case? I cannot give them, because if I have to give the new IP address of the master instance, then I have to redeploy all the other pods, which is practically not possible. Second thing is, how do I use the what if I use the host names? Let's say I use the host name of the first instance so that my other instances can replicate the data from. But as I said, if this pod restarts, even this identification changes because the hash will change. So which means my replication algorithm will only work if I know the master IP address, or if I can set the host name of the particular pod to a stable or a static one. In case of deployment, both are not possible. We know that IP is never possible because IPs change, but in case of deployments, these names will keep on changing. So I cannot use a static reference point so that the other pods can actually replicate the data from. So this is not at all possible in case of deployments. So how it is possible in case of your stateful sets? So how stateful sets, in stateful set your other instances can read from the master so that they can replicate the data. So stateful set supports sticky identity or the host name. So in case if you are using stateful sets, so I'm going to show the stateful set, the definition file of stateful set. In case of stateful set, every replica in the stateful set gets a unique identification, that is the name of the stateful set and the ordinal number which starts from 0. So every pod will get the ordinal number starting from 0 and it will be incremented by 1. So if I have a stateful set with 5 different replicas, so they will be like a stateful set name -0, 1, 2, 3, 4 and 5. Here I'm getting a name, so which is stable, and also here, even though if one of the particular pod restarts or reschedules due to some issue, they are going to get with the they're going to come up with the same name. That means I have a stable identification which is not going to change across pod restarts. Anyways, we are not going to use the IP addresses because IP address we know that they change, but here the name of the pods will not change. So which means I can ask this pod and this pod to talk to this pod using a stable name, so that even if this comes up in another node, or if it restarts due to some issue, it will come up with the same name, so that my MySQL 1 and 2 pods will always establish a communication to this particular pod. But how do they establish a communication? So here we can take these as replicas, and I can take this as primary database. So how do my replicas will talk to primary database using its name of the pod? So we said that name of the pod is not possible because pod to pod DNS resolution is not possible. So we have the DNS resolution, but the FQDN will have the pod IP address. So we came back to 0 again. So we cannot use the IP address. Then how do I use this stable name so that other replicas can talk to this particular primary pod? So this is where I will use the I'll need the headless services. So before that, so how do we write the data to only primary database? So how do I just how do I target this particular pod, or else how do these replicas will talk to this primary pod to replicate the data from? So should I use the name of the pod? No, name of the pod is not possible because pod to pod communication is not possible. So should I use the cluster IP service? So what if I use cluster IP service? Let's say the first question is I wanted to write some data to this primary database. So if I have a client something here, a client pod which is MySQL client, and if MySQL client has to talk to MySQL 0 to write the data, let's assume I create a cluster IP service. So the request will come to the cluster IP service, and cluster IP service, since there are 3 pods, okay, what cluster IP service will do? So it will again do the same thing, that is, it will load balance the request. That means it may send the read operation to different pods at different requests. So using through cluster IP service, will I be able to target a single pod? No, it will always be load balanced. Then what to do? So do we use headless service? No, still, even if I use headless service here, and if I have another pod to talk to the headless service will still forward the traffic to any of these backend instances, but this time we are calling it as DNS round robin load balancing. Then how do I just target this pod? So if I directly use the client, and if I directly wants to talk to this pod for the write operation, so how do I use this? So this is where your headless service comes into the picture. Your headless service, when combined with stateful set, every pod will get a unique FQDN, which is a combination of the pod name, which is managed by the stateful set controller, and the headless service that we are going to use for that stateful application, or the stateful set controller. So this is the name of the pod. So MySQL -0. So the next pod gets the unique identification MySQL -1 -2, and with the name of the headless service, I can take this particular part as the fully qualified domain name, which means if this pod A wants to talk to this particular pod, I can use the name of the pod followed by the name of the headless service. If let's assume my request is only this, let's forget about this, let's say it is http:// headless service. In this case, if your request go to the headless service, it will always redirect the request in a round robin fashion. But if I use this pod without any headless service name, this is not possible, because http:// MySQL -0 doesn't DNS resolve to the IP address of the pod, because that is not there. Only if I use the DNS, if I use the cluster IP service name, that gets resolved to the cluster IP. But if I use the direct IP, the name of the pod, it won't resolve. But if I combine the name of the pod dot the headless service, I can simply target this pod. If I want to target this pod, I can simply use MySQL -2 dot headless service. So this one will be the request. That means the pod A, if it uses this HTTP call, will always redirect the request to this one, which means for write operation, I can use this request to always target this. But what about the read operations? So in case of read operations, in many scenarios, so there will be another service created. In case of write operations, I'll use the headless service, because headless service gets a gives a unique FQDN for each pod of the stateful set controller. In this case, if I use the headless service followed by the name of the pod, I can basically target a single pod. So here I gave a wrong one. So here this is actually the write request, and this is basically the read. But how do I read the data in this case? So in many cases you will see two different types of services. One is the headless service for the databases or the stateful sets, and the other one is the cluster IP services for the databases. Why I need two different services? Because with this headless service I can target a single pod. So here with the headless service, with the name of the pod, I can use this request to always target the first pod. But in case of read, I can directly send the read request to the headless service and it will load balance the request, or else I can create a cluster IP service and I can use the cluster IP, the name of the cluster IP service followed by the incoming port of the cluster IP service. Then any request comes to this service will always be load balanced across all the backend instances. So for headless I can use to write, and for cluster IP and for the read operations I can use the cluster IP, because cluster IP will always load balance the request. Since once I write the data here and all the other pods gets replicate the data from the other ones, so I can read the read operation because already the data got replicated. So in case of your stateful applications, so your stateful set controller is going to give you persistent identities. That is, it is going to give you the stable host names and IP addresses. So the reason why we need stable host names is to uniquely identify a particular pod. But in case if we are using the deployment, so these are going to get the random names and random hashes, so which we cannot have. So the first pod in the stateful set controller, we will usually take both read and write requests, but all the other pods will take the read requests only, because if I have three different replicas, 1, 2 and 3, so I always want to write to first instance and I can make others to read the data from the first one. So here I can use even one as the read operations, because data is here and it is replicated here, it is replicated here. So even replication becomes easier for me. So a data returned to a first pod can now be easily replicated by other pods, because the name is static here and these names are persistent even across pod restarts. So this is how even replication can also work. And every pod of your stateful set should have a persistent storages, because so these are the databases. So anything that you write to a database container will stay in that container, and if that database container is restarted or if it is killed and got scheduled on another node, the data that is within that container file system will be destroyed. So that means whatever data that you have within this container file system has to be backed up. So here we are going to use the persistent storage solutions like PVCs, where we create a storage which is a PVC and mount it into the container at a specific location where your container is expected to write the data. Let's say that your database is writing the data to something like varlib data. So this is where actually your container is storing all the information about the database. Now I can take a PVC, mount into that location, so that any data that your container writes to that location will be automatically backed up into the PVCs. Now here every replica of your database is an individual pod. So every pod should have its own PVC. Since a data the write operations that we the data that we write into the primary instance will be automatically replicated by the secondary instances, so they will also have the PVCs which is almost holding this, which is holding the same data. So here MySQL 1 can replicate the data, and also MySQL 2 can replicate the data from MySQL 0, because MySQL 1 can talk to MySQL 0 which we with the name with the FQDN, which is a combination of the name of the pod followed by the headless service. So this is a headless service, so which means MySQL 1 can target MySQL 0 and MySQL 2 can also target MySQL 0. But in this case your replication algorithm will not work like this. The best way is 1 can replicate from 0 and 2 can replicate from 1. So this is how the replication algorithm should be set up. And every PVC is taken from a PV, that is persistent volume, which is either provisioned statically or it is provisioned dynamically by using storage classes, which you are going to see. But the only thing we need to remember is that every stateful set pod should have a backend PVCs to persist the data. Now, order creation, deletion and upgrades. So why we need order creation, deletion and upgrades in case of stateful application? So let's say that I have a MySQL database of one replica. So I only have one database replica. So this database replica is taking the both read and write operations. Now, if I increase the replica from 1 to 3, so what will happen in case of deployments? In case of deployment, the remaining 2 replicas will be started at the same time. So that means second replica and third replica will start at the same time, getting unique pod names and unique IP addresses. But in case of databases, it is quite different, because your databases has to persist the data and they have to have the correct data. Let's assume I have only one replica which is having which is taking the read and write operations, and this primary database has some 10 user account information. Now I've increased from 1 to, let's say, 3 replicas of my database. So if I increase to all 3, so what will happen is, so let's say in case of deployment, 2 and 3 replicas created at the same time. Now when they create at the same time, since these are the databases, they should have the latest data also. Otherwise, write operations will lead to different outputs. Okay, because so let's say I have 3 replicas now, and if the user sends a read request, so this read request has to be redirected to any of these backend pods. So if the data is available here and these are not available here, so reads won't be successful. So in case of stateful applications or through a stateful set controller, so the scaling will be one after the other. That means the ordered scaling. So if I increase the replicas from 1 to 3, not 2 and 3 will be created at the same time. Here the second replica will be created first, and when it is created, it will always replicate the data from first. That means this is the this is the first replica, and when second replica comes up, it will replicate the data from 2 and it will sync up all the data. So your second replica will also have the latest data from your primary. Now it will increase from 2 to 3. So when it is increasing from 2 to 3, it will also make sure that it replicates the data from the second, because second has the latest data when it try to create when it try to sync the data from the first. So it is called order creation, where when you create the replicas, it will always create one after the other, not all at the same time. And when they are created, they'll also replicate the data from the previous pod. And also in case of deletion, so let's say that I have 3 replicas of the databases running, and I wanted to scale down to 1. So in case of your deployment, any of the random pods will be deleted. So in case if you want to go from 3 to 1, so any of the 2 replicas will be randomly chosen and deleted. But in case of your databases, your first pod is always acting like a primary, which is always taking the write operations, which means if you are scaling down from 1 to 3, you should not delete your primary database. You should leave that and you should delete the rest of the instances, because rest of them are acting like the read replicas. So they are only meant to read the data, to serve the read request from the user. So that's why in case of stateful set, it is ordered deletion. In case of deletion, it will always come from the last instance. So if I'm scaling down from 3 to 1, first the last instance will be deleted, followed by the other instance. So in case if you are scaling down from 3 to 0, so obviously the first one will also be deleted, but the scale down is from the last instance. So in short, stateful sets are valuable for applications that requires one or more of the following. The first one is stable unique network identifiers. So in case of stateful sets, in case of databases, so we always want the primary database to take the write request and all the secondary or the read replicas to serve the read request. So in case of reading the request, I want the data which is returned to primary to be replicated by all the second instances. So if I don't have a static name, so the secondary replicas will lose the connection with the primary. So in case of deployments, all the names are random in nature, but in case of stateful sets, each gets the unique identification in the form of stateful set name followed by the ordinal index which starts from 0. So I can take the database I can take the pod with -0 as the master. So all the slaves can use this -0 as the identifier to replicate the data from. So this is the first advantage. And all the stateful set pods should have the stable and persistent storage, because so we are going to talk about the databases, right? We are dealing with the databases. That means the data which is written to the container file system has to be backed up, otherwise you will lose the precious data. And also ordered graceful deployments and scaling. So as I said, so when you're scaling up, you will be scaling one after the other, not all at once. So if you have 1 replicas and if you wanted to scale to 5, in case of deployments, all the replicas, the missing replicas will be created at the same time. But in case of your stateful set, so the scaling will happen one after the other. Even in case of scale down, so the instances will be deleted from the last. And also ordered and automated rolling upgrades, which we already discussed. But still we need to talk about few more concepts in case of stateful sets, which are volumes, persistent volume claims, and storage classes. Pods are ephemeral in nature. Each container in a pod has its own file system that usually comes from the container image. So if you already created Docker images through Docker files, so you might have created a custom image in which you will put some custom data. So every container in a pod has its own isolated file system that usually comes from the file system that you have created. And each time the container gets restarted due to some issue, so the file system is also reset, which means all the logs or any data that you put or write within the container, they gets reset because you are not persisting the data. So how do you make sure that the container's data is persisted? That means anything that is written into a container are still available beyond the life cycle of that of a container. So we'll see that using volumes. There are basically 2 types of volumes depending upon the life cycle. So some volumes are created when the pod is started and they are destroyed when the pod is deleted. So they have the same life cycle as of a pod, which means as long as the pod is running, you have that volume access. But as the pod is deleted, all the data that is written within that volume is destroyed. But why do you need such kind of volumes where your data cannot be persist beyond the life cycle of a pod? We'll understand that in some time. But in case of some volumes, they have the life cycle beyond that of a pod and also of the Kubernetes node itself, which means even if the pod is deleted, you still have the data. And even though if the Kubernetes node is deleted, you still have the data. So volume is essentially a data directory that you map into a container. So this is just a directory that I created within a pod, but I mounted it into C1 and C2. So whatever C1 writes to the SEM storage, I can access it from C2 container because both mounted the same volume. Here, as we said, that containers are ephemeral in nature. So when they are destroyed, so the content that they have inside it is destroyed. But here, since I mapped this particular volume into the container and I made sure that the container C1 writes only to that mount, which means it is writing the data to the STEM storage. So even if the container restarts or killed or restarted, it can still access this data because it is going to mount the same volume again and again. But since these are within the pod, if the pod itself is destroyed, the temp storage contents will also be destroyed. Docker has also a similar concept called Docker volumes. There are 2 types of volumes in Docker, known as named mount and bind mount, so which usually persists the data, that is containers data. Ephemeral versus durable volumes. So we can have volumes shared across various containers in the pod, as I said. So these are called ephemeral in nature because they share the same life cycle as that of a pod. So they have the life cycle as of a pod, which means when the pod is destroyed, even the contents inside the STEM storage will be destroyed. But in what scenario? So if, let's say that you have multiple containers in a pod and these multiple containers should share the data. So in this case, you can create a temp volume and then you can mount it mount it to all the available containers for them to share the volume, share the data. So these are called ephemeral volumes. We have MTDR, which is of type temp. So if you need the data to be persist beyond the life cycle of a pod, you can go for persistent volumes, also known as durable volumes. The persistent volume is a storage object that lives at the cluster level. So this is not tied to a single pod or a single node. So this is at the cluster level storage, which means even if the pods are killed, you still have the data. Example of that persistent volumes are host path and persistent volume claims, which are going to see now. So MTDR, it is a temp storage which will be created within your pod, and this will be created when the pod is first created. So it will have the same lifetime of a pod, so it gets destroyed with pod deletion. And MTDR is stored in whatever medium that is backing up. Since pod itself is a virtual component, as we all know, pod is nothing but collection of containers. But where exactly this MTDR volume will get created, because this is not getting created in any containers file system. So this is getting created in the pod, but where exactly? So you can set it to get created at the RAM or any SSD or any network storage by setting the mtdr.medium type. So usually it will be created in RAM if it is not set under the volumes here. And here I can create the volumes, so which is at the spec level, and the name of the volume is mtdr, as you can see, and the name of the mtdr is HTML files. So this volume can be mounted by n number of containers. Here I have two different containers that can map the volume. Under the containers here, I have one container called web server. This is using the volume mounts option to mount the volume which I created into this particular location. So this means if this container writes anything to this location, that means I'm writing it to my mtdr, because I took this mtdr and I mounted it into this particular path. So in case of host path, so this is a durable volume. This is a sort of persistent volume, but so there is a small catch here. Here host path refers to a path on the host or the node in which this pod is created. Your Kubernetes might have hundreds of nodes, okay, which means if the pod is created in a node called node 1, so this host path volume will also be created in the same node. So this is outside the pod, and this is at the host level. That means if you're using Linux, it is at the Linux host level. And since this is created at the host level, I can use the same mounts. So I can use I can mount them to individual containers. Individual containers can share the data through this host path. But here we need to use them with caution, because next time if this pod gets scheduled onto some other node, and if the some other node doesn't have this folder that is created, so your container will not get the actual data, because actual data is in the another node. So that's the reason why it is named as host path, because it is a path on a specific host. The pod gets rescheduled, and if the data is not available in the new node, your data is going to, your containers are going to start from scratch. So here I can create a volume. The name of the volume is this, and the type is host path. So I'm using the path as /temp. That means this directory will be created in /temp. And volumes, anyways, I can use it in all the containers in a pod through volume mounts. So I'm mounting the host path volume which I just created under /cache. So whatever your container writes under /cache usually gets written to this host path volume which is under /temp. Since we are going to see all these in a separate section, so we are skipping. So this is fine. So we are using mtdr, but the life cycle of mtdr is at the pod level. So if the pod is deleted, your data is gone. But in case of host path, the data is still persist at the host level, but if the pod gets rescheduled onto some other node, you will not have access to this data. And also the node which is storing this data, if it is just due to some reason, your data is gone. Managing storage is very distinct problem inside a cluster. You cannot rely on any of these like mtdr or the host path for persistent data, because mtdr data gets lost when the pod is deleted. Host path data will be persist at the host level itself. If the pod is rescheduled or if the node is destroyed, your data is gone. And also provisioning a cloud volumes like EBS in AWS or Azure Disk often tends to be complex because of the complex configuration. You can also use the cloud providers volumes, but the configuration is little bit a complex side, which means you should also know how these volumes should be provisioned and consumed within your Kubernetes environment, which is not at all an easier task, because using cloud volumes, in the sense you're not attaching this volume to a particular node or into a particular pod, because these volumes are at the cloud level, so deletion isn't possible directly from the cluster. But using these is a little bit complex. So to overcome this, we have persistent volume subsystem provided by Kubernetes for all the users and administrators to abstract details of how storage is provided from how it is consumed. Here, if the developer has to know how to use this cloud storage volumes to persist the data beyond that of cluster or the pod, he has to know how to actually create that volume and mount it. But these details are complex. So what Kubernetes provides is, Kubernetes provides a persistent volume API, so which makes it easier to provision that storage for us, and also how to consume that storage by developers. So for both administrators and both for the developers, it makes it easier in the form of two API resources, which are persistent volumes and persistent volume claims. Let's see how these are different. So we know that we cannot use mtdr and host path, and at the same time we can go for to overcome these issues, we can go for external storage volume types like the AWS Elastic Block Store or Azure Disk or GCP Persistent Disk or NFS storage. But developers must know the knowledge on how to provision the volumes from these storage providers. It means the developer has to know the information about these volumes, like the EBS ID, the file type to use. So this is little bit difficult for the developers to use in their applications. So Kubernetes solves them by using persistent volumes and claims, by decoupling how this storage is provisioned and how the storage is being consumed. Admin basically creates a pool of persistent volumes. So this is just the task of the the administrator. So it creates a PVs for the users to choose from. So as the user means as a developer. So persistent volumes are the volumes that are created. So they have various specifications, like from where they are taken. So I can create a persistent volume from an NFS or from ISCSI or some GCP, AWS, and he makes them available to the cluster. So he will provide multiple PVs with varying properties like the performance, sizes, etc. So one PV he can create from SSD, one PV he can create from HDD, one PV he can create from NFS. So I have various choices. So depending upon the choice, depending upon my application, I might use specific PV. It's cluster-wide resource used by user to store or persist data beyond the lifecycle of a pod. Now, as a developer, what I can do is I can take a PV and I can create a PVC or a claim. So which means developer will claim that storage from the underlying PV, and that claim he is going to use it within the pod. It is just like a mount. So he is going to mount the claim inside the pod, specifically inside the containers file system. Now the container will write it to this claim. Since this claim is taken from PV, your data is safe in the PV over here. So it is just like plugging different storages. Like you can create PV from AWS, from GCP, from NFS, from local storage disk. So whatever it is, so it is available at the cluster level. So PV is not backed by any locally attached storage or any worker node. As we said, these are by network storage subsystems such as cloud providers storage or network file system, or any distributed file system like Ceph or GlusterFS, which means these storages are not tied to a single worker node, which means they have the life cycle beyond that of a worker node. They provide the same file system that can be mounted to the cluster without being associated with any particular node. So here even deleting node will not affect your persistent volumes. Here you can also increase the size of the persistent volumes. Let's say that the persistent size volume size is not sufficient, you can also resize it. That means you can increase the size, but decrease isn't possible. So this is how you create a persistent volume. So I have the API, persistent volume API, and the name I am using is PV-volume1. So I'll talk about storage classes in some time. So its capacity is 1G. So this is the PV and it is having 1G. So it has some access modes. We'll see what are these access modes. And here it also has a reclaim policy. Again we'll see. So this defines from where this particular PV is provisioned. So I am provisioning this PV from host path, which is actually not the correct way, because we need to use the cloud providers APIs to actually create the PVs. And here I have a storage class which is empty or none, and I have a storage class which is slow. So which means I created a PV, two PVs, one with the empty storage class and the other one is the slow storage class. So if my developer needs a PVC, which is persistent volume claim of, let's say, 500 MI, so all he has to do is he has to mention the storage class name. Let's say he has used his storage class name as slow. Then your PVC will be bound to a PV with the matching storage class, and this 500 MB will be taken from this capacity 10 GB. Okay, so a cluster administrator creates PVs with different sizes and access modes. So you may have hundreds of PVs, PV with different sizes, different access modes, different recycle policies and all. So you have to see how much you need and what is the access mode. Then immediately your Kubernetes will create this claim by checking all the PVs. So once a PV is matched with your requirement, your PV and PVC are bound together. So this is how your PVCs are created. So once you have the PVCs which are created from a matching PV, so you can automatically use this PVC and mount it into a particular container and use as the backup. So whatever you write into this PVC gets automatically stored in your PV. So if I take this as a PV object where I have the storage of 100 MI, and this storage class's name is manual. So this is how I've created a PV. So now I can create a persistent volume claim. This is the name. So when I'm requesting for 100 MI storage, so what I'm doing is I'm also requesting for a specific access mode and also a particular storage class name. So this PVC basically will be looking at the storage class name. So it will choose a storage class name from a particular PV. So if the storage class name is already available and if there is a sufficient storage here, so I'm requesting for 10 MI. So this particular storage class name manual has 100 MI. So automatically this PVC claim of 10 MB will be taken from this persistent volume which is having 100 MB. So how the claim will be established is, so your storage classes are combined. So your Kubernetes will check what all PVs can provide my claim of 100 MI. Then automatically those will be bound together. So this is how the arrangement looks like. So you have your deployments will have PVCs, and these PVCs are bound to a single PV. So these PV are the actual storage units, right? So they can be physical disk or they can be cloud providers storages, depending upon the configuration you write. And we also said that every persistent volume can be mounted onto a host in any of the supported and as we already discussed, persistent volumes can be mounted on a host in any way supported by your resource provider, which means supported by your cloud provider or your Ceph or GlusterFS or NFS file system, etc. And each cloud provider or the resource provider will also support different access modes. Let's say you are using NFS as the persistent volume. NFS volumes can support multiple read-write clients. That means they can take multiple reads and writes at the same time. But let's say you a specific NFS mount, you want it to be exported as only read only, which means another nodes can mount this NFS as only read only, which means you cannot write anything into that NFS mount. So each PV gets its own set of access modes. So you can create a PV and you can also set different access modes. Let's say if I have a PV with read write once as the access mode, which means read write once, only single worker node can mount the volume. Okay, if I have 100 nodes, not all 100 nodes can mount this. So only one worker node can mount it for reading and writing, because it is read write once. So since only one worker node mounted it, any pods running in that worker node only can access this mount. So pods which are running on another mounts on another nodes cannot access this particular mount. But in case of read only many, in this case your persistent volume, whatever you created, can be mounted by all the nodes in your Kubernetes cluster, but all can act like read only, which means if I create a PVC and if I mount it into a particular container, it can be only read only, so you cannot write. In case of read write many, the volume can be mounted as read write by multiple nodes at the same time. So these are the access modes. So in case of reclaim policy, so we said that PVC will be taken from a PV. So what will happen if I delete the PVC object? That means if I delete the claim, so what happens to the actual content that is written in PV? So there are two different types of reclaim policies. One is delete. So which means if the PVC is deleted, so whatever the data that is stored in PV will also be cleared. In case of return, persistent volume contents are still be retained even after associated PVC is deleted. In this case, these PVC contents are to be manually cleared by the cluster administrator. And now we said that the administrator can provide different sort of PVCs backed by different access modes, storage classes, or reclaim policies. So are there any other ways instead of apart from creating PVCs manually? So are there any other ways of dynamically creating PV and PVCs? Yes, there are actually two ways to provision a persistent volume. The first one is static provisioning, where your cluster administrator actually creates these PVCs depending upon the various parameters like the sizes, the access modes, etc. So in case if I have a PV of let's say 100 GB, I can create a PVC of till 100 GB. So in case if my requirement is, let's say 101 GB, and let's assume there are no PVs that can give my claim of 101 GB, or that can provide me a claim of 101 GB. So what will happen in this case? So there are two ways. So I can ask my administrator to create a new PV with my requirements, or else I can use storage classes. So here, as I said, when we talked about storage classes here, so here every PV comes under a storage class. So what are these storage classes? Here the storage classes are special APIs where they support dynamic provisioning of PV. So in case if my PVC doesn't find the matching PV, what my storage class can do is storage can automatically provision a PV for me with my matching PVC's requirement, and automatically my PVC will be claimed with the newly created PV. So this is all dynamic in nature. So in case of these storage classes, so the administrator will create a storage class with the details of the cloud provider. So usually let's say that if I name the storage class as like fast, then in the storage class definition I can put the details of my AWS provisioner details. Then any PVCs that uses this fast as the storage class, automatically my PV will be dynamically created depending upon the PVC's requirement, and that PV is bound to that PVCs. So this is the use of storage classes, where it will automatically allow me to dynamically provision the PV for my PVC's requirements. And most of the clusters will always have the default storage class. In fact, Minikube also provides a default storage class of host path type. But why these PVCs are needed, and why storage classes are needed in case of stateful sets? So in case of stateful sets, we said that we'll be deploying databases or stateful applications with multiple replicas. Now we said that each replica will in turn needs a backend PVC to persist the data. So how do these PVCs are created? So these PVCs are created dynamically through storage classes. So if I have the PVCs already available, I mean if I have PV that can give these this can support these PVCs, that is fine. Otherwise what I can do is I can use volume claim templates. So here this is the stateful set. So stateful set has certain replicas, so I need 2 replicas under this stateful set. So here each replica needs a PVC. So what I can do is I can create a volume claims part here, and the name of this volume claim template is www, and I'm using the access modes and the storage class name. So here this is commented out, but if I use a storage class name here and if I request for 10 MI, so what will happen is your Kubernetes will automatically provision these PVCs of 10 MI each depending upon the storage class. So automatically your PV are provisioned first with the same storage as the PVC, and then that PVC will be bound to this PVC. PV is bound to that PVC. Yeah, this is the advantage of storage class. So automatically, so depending upon the number of replicas, those number of PVCs will be automatically provisioned through volume claim templates, and each volume claim will have a unique naming convention, which is a volume claim template name followed by your pod name, that is the stateful set name, and the pod name plus the ordinal number. I'll show that in the demo. So it will have the combination. So if the volume claim template is www, and if the pod name is MySQL-0, and the ordinal number it is 0. So I mean the ordinal number, it's the same thing, right? So it is www.-MySQL0. So this is the unique identification of each pod inside the stateful set, and this is the volume claim template name. So this is about the various concepts that we are going to see in the demo. Now let's see how to practically understand the deployment controller, stateful set, headless services and all. So here I have various examples, and all these examples will be uploaded to a Git repository. So I have the Flask based application deployment and also the Nginx stateful sets. So for each of these concepts we are also going to refer the official documentation and see the the official theory part as well. But since deployments doesn't need any extra introduction, we are going to see this practically. So I have this readme file that explains the commands that I'm going to use for this demo. So this is the web.yaml file, which is the deployment file. So I have this deployment which is named as Flask with 3 replicas, and these are the template. This is the pod template section, and each pod gets a label called app:/Flask, and in the spec of the container, this is the name of the container, and this is the Docker image, and the container port is 5000. And here I'm going to create 2 different services here. So the first service is a normal service, and the next one is a headless service. So this service is Flask normal, and the incoming port of the service is 80, and the target port is 5000, which actually matches the containers port. And the selector, I'm using the same labels of the ports. So this is just the normal service. And in case of headless service, just the name is changed here, and the cluster IP is set as none in case of headless service. This is the only change, and the rest of the configuration, that is the ports part and the selector part, it is same. So basically what we are doing is we are creating so let me draw in the whiteboard and show you. So here I have Flask application with 3 replicas, and all these are deployed through a deployment controller. And I have a cluster IP service, and this cluster IP service is using the labels of the pods. And I have the headless service, which is again using the same labels of the pods, all these backend pods. Here in the headless service, I just mentioned the IP or IP of this cluster IP is set to none. So which means this has become a headless service. So here I have different names as well. Since I'm already using the Minikube cluster and it is already up and running, so what I'm going to do is I'm going to just apply this web.yaml file, and let's see what will happen in case of using headless services and in case of using cluster IP services. So here under the Flask deployment, so I have this web.yaml file, So I'm applying web.yaml file. So there are two services created. One is the normal service, the other one is the headless service, and I have a deployment of three different pods. So what I'm going to do now is I'm going to just get all the pods and these services. So there will be three pods. As you can see, these are managed by a deployment controller. So with the name of the deployment and the replica set hash, and as well as the pod hash. And here I have the headless service with cluster IP set to none, and also the normal service with the cluster IP set to the actual cluster IP. So let's wait until our containers are in the creation state. So the containers are in the creation state, and as you can see, the name of the pods are actually random. So if I can get the replica set, so you can also see the replica set hash. So this hash will also be appended with the pod name. So that's the reason why we cannot use the name of the pods as an identifier in case of a deployment, because these names keep changing with every pod restart. Let's now what we'll do is, since I have the cluster IP service and headless service, so I wanted to show you the difference between them. So I'll create a client pod here, and now from within this dummy pod, I'm going to DNS lookup this cluster IP service, at the same time DNS lookup this headless service. So for this I'm going to use a test pod. So for the DNS resolution, that means just checking the DNS query, I'm going to use the BusyBox 1.28, and I just wanted to see the responses by running the curl request. So for this I'm going to use the Nginx Alpine. The reason why I'm not using both is, so one doesn't have the curl and the other doesn't have this NS lookup. So that's the reason why I'm using two separate images. So what I'm going to do is I'm going to run this as the test pod with -it and restart policy set as never and -rm. So the reason why I'm using -rm is I don't want this pod to be existing in my cluster as soon as I exit from it. Since the BusyBox, the starting process is sh, as soon as you write as soon as you initiate this command, so you'll be entered into the cell session within this particular pod. So I'm within this pod. So within this pod, what I'm trying to do is I'm just using NS lookup on the cluster IP name. So the cluster IP name is Flask normal. So what I'm going to do is I'm going to use NS lookup and the normal service name. So as I said, normal service should always return the name or the IP of the service. So here the cluster IP service IP address is this. So your DNS lookup of the cluster IP service name should always return the cluster IP, and you should also give the port number. So in the pod definition file, I use the incoming port as 80, so colon 80. Even if you don't put it, is fine. So if I run NS lookup, yeah, as you can see, the DNS lookup will first go to the core DNS service name, which is in the kube system namespace, and from here from there it is going to just send the resolve the cluster IP of the cluster IP service. Since this is the IP, you can see the same response here, which means if I am just sending the request to cluster IP service, cluster IP is going to just respond with its own IP apart from the IPs of the pods that is backing it up. So this is the actual proof, and this is the Flask services FQDN. But if I use the same NS lookup on the headless service, the responses will be completely different. So here, as you see, the responses are multiple responses. So here when I use NS lookup on the Flask headless service, which is type cluster IP set to none, which is headless service, I'm getting the individual pod IP addresses. So I'm getting the pod IP of this pod. Next, there are 3 pods, so obviously you'll get 3 different responses. And as I said, any pod that is managed by the headless service gets the FQDN in the form of the pod IP followed by the name of the actual service. But here these names are actually random, so the pod IPs are random, so you cannot rely on the FQDNs of this particular pod. but if I have to talk to the individual pods, since I now I got the IPs of the individual pods, I can immediately target the individual pods. So if I have curl here, since curl is not here, so now since I got the IPs of the individual pods, if I want, I can talk to the individual pods using its IP address directly. So every time if I want to get the IP address of the backend pods, all I do is I'll just use the IP from this particular DNS response and I can connect back. But there is a small misconception that here when you talk to the headless service, it will load balance the request. But if you talk to the cluster IP service, it will load balance the request. But if you talk to headless service, there is a small misconception that it will always go to the first pod. So there is a small misconception. So let's prove that this is wrong. So your headless service still will load balance the request among across all the backend instances. So let's prove that. For proving this, what I'm going to do is I'm going to create one more dummy pod with Nginx Alpine as the image, because this image has the actual curl utility in it. So what I'm going to do is I'm going to just use curl, and then I'll just curl on the normal service name. And as I said, so you should also care about the incoming port. So flask-normal, and then the incoming port of the Flask normal. So Flask normal is the cluster IP service, and the incoming port is 80. So all I'm going to do is I'm going to use 80. So if you see here, every time when I send the request to that service, it is giving me a different response. That means it is load balancing the request, as we know. But in case if I use the same Flask headless as the service, and remember here, if you are directly talking to the headless service, and if the headless service has an incoming port, you cannot use that. You should use the target port by directly targeting your backend ports. So here we are targeting the backend ports, and the ports have this pod of 5000. So here if I use the headless service name, so there is a misconception that it always forwards the request to the first instance, but it's not. So let's see the responses. So here I'm getting 5, here I'm getting 3. So you can see the responses are completely changing, which means it is not redirecting to a specific instance here. So this is the use of headless service. Here headless service returns the IP address of the individual pods, but here but if you talk to the headless service, it is still going to load balance the request. It's not like it always targets the first pod. But there is a use case with headless service. The headless services are to be used with stateful sets to get unique identity to each and every pod in the form of pod name dot headless service name, which we are going to see in some time. So all I'm going to do is I'm going to delete this YAML file, which is web.yaml. And now before going into the stateful sets, let's go to the official documentation and see what are stateful sets. So we already talked about stateful sets. Unlike deployments that generates random pods names, here stateful set generates stable names through each and every pod. So it becomes easy to identify the master pod by all the slave pods, because here every pod gets a static name. And now how do I write this stateful set? It is just like a deployment. So if you replace the kind stateful set with deployment, everything will be same. So you will have the template, spec section, everything. But another thing that differentiates deployment and stateful set is use of the this service name here. So here in the spec section, I should use a service name. This is actually the headless service name that you're creating to embed or to be used with this stateful set. So here I have this service with cluster IP set to none, which is a headless service with the name called Nginx. So I'm using the same service name in stateful sets, which means every pod within the stateful set gets a unique identification in the form of the name of the pod. The name of the pod is web-0, web-1, web-2, depending upon the replicas, followed by the name of the service, which means if I have to directly talk to this pod, the first pod of the stateful set, I can say it is web-0 dot nginx. So that gives the unique identification. And also, as we said, that every stateful set pod, every pod in that stateful set gets an unique identification, unique persistent volume. So what I can do is I can create persistent volume claims at the spec level, at this spec level, and these volume claim templates define the storage class using which or from which your PVCs will be created. So using the storage class, first your PV objects will be automatically provisioned depending upon the amount of requests, amount of storage you are requesting, and the automatically provisioned PVCs will be attached to each PVC. So here I have 3 replicas, so 3 PVCs will be created with the name of your volume claim template name hyphen followed by your pod name. So this is about the stateful set. So for this demo, what we are going to do is, so I'm going to show you the nginx stateful set. So here persistent volume claims are you can ignore if you are just learning stateful sets, or if you already have the storage class defined in your cluster. In that case, you can use the volume claim templates, but these volume claim templates are needed only when you try to mount that PVC that you created. So here I have an nginx stateful set, and I have a service which is called nginx headless, and the cluster IP set to none for this nginx service. And I also have the normal service just created in case if I want to show you the difference here as well. So same configuration for ports and the selector. Only thing is cluster IP set to none in case of headless services. In case of normal services, it is not set to none. And here I created a stateful set controller with the name as web. And here the service name, I'm using the same service name that I created the headless service. Replicas are 2, and here I have the selector template, which is a pod template. And so what I'm doing here is I'm creating PVCs through persistent volume claim templates. And here I have access mode set to this, and there will be 2 PVCs created because there are 2 replicas. What I'm doing is I'm mounting those volumes that are created PVCs under this path, user share nginx HTML, and I have some data automatically created. So here I have a stateful set of nginx. So for every nginx instance, what I'm going to do is I'm going to create index.html file, so a different index.html for each replica. So dynamically I'm generating this, that is hello from container, and the container name I'm redirecting it to the index.html file. So index.html file, I'm creating this particular file in the init container. So in the init container, so I'm mounting this particular volume that I created as the mtdir, because this is the shared volume. So mtdir I'm creating, and in the mtdir I'm creating this index.html file, which is getting mounted into my actual container at this path, user share nginx HTML. So which means the init container first will generate the index.html file, which will actually replace the nginx container's index.html file. For replacing, I am taking the mtdir volume, and the same volume will be mounted in the init container. At the same time, it will be mounted to the main application container, thus replacing the index.html file in the main container. So the volume time I'm using as mtdir because this is just a temporary storage, but in order to persist the actual data under user share nginx, I am mounting that in the PVCs. So this complete path, user share nginx HTML, will be backed up in each PVC. So this is the actual definition of the stateful set. So if you want to know more information, you can refer the actual documentation. So now what we are going to do is we are going to run this file, which is web.yaml file. So just apply this file. So nginx stateful sets, so it is web.yaml file. So I have a stateful set created and an nginx normal service and nginx HTML service. So if I use kubectl get sts, I'm going to get all these stateful sets. So there is a stateful set, but none of the replicas are ready. So let's just use kubectl get pod. Okay, so here the pod is in the initialization state because the init containers are still running, and they are generating the content, that is dynamic index.html content. See here one advantage of its stateful sets again. So here when I created two replicas of the stateful set, those are not created at the same time. So first instance should be ready, and after that only your second instance should be ready. So in case of actual databases, when your the first instance has the data, and if you scale it to 2, the second one will try to scale up. While scaling up, it will replicate the data from the first. Let's say you're scaling from 1 to 3. So second instance will come up by replicating data from the first, and the third one will come after the second one is ready, and it will replicate the data from the second one. So this is called order creation. So now both the pods in the actual stateful set are up, and if you also see the storage classes, since I'm in the Minikube cluster, I already have the storage class, which is a standard storage class. So this has reclaim policy of delete, and so from here volume claim templates are provisioned. So you can also get the total PVCs here. So there are a lot of PVCs, but if you see the ones which are created today, there are only 2 of them, and you can also see they have capacity of 10 MI because I requested a PVC size of 10 MI. So PVCs will be automatically provisioned through storage class, and those PVs will automatically get attached to the PVCs. Sorry, it's other way around. Actually PVCs will get attached to the PV. So you can also see the 2 PVCs which we just created with the same size 10 MI, and the naming also you can see. So the naming is the volume claim template name followed by the actual pod that is using it. So even your pod is deleted or relocated due to any issue, that pod will get still get attached to the same PVC which it was attached to before its deletion or before it was relocated. So that is advantage of using stateful set. Each pod will get its own PVC, and each pod will get a unique identity, and that unique identity will stay even if the pod is restarted n number of times. But that's not the only thing that we will test it now. So first what we wanted to do is we wanted to see 2 different things here. The first thing is we are again going to do ns lookup and see what are the responses that we are going to get when we use the DNS name of your normal service name and the DNS name of your actual headless service name. So for this I'm going to start the BusyBox image again, and now I'll use ns lookup and the name of the normal service, which is nginx-normal. So here I'm, as usual, I'm getting the cluster IP of the normal service, but if I use the headless service, then you can see basically it is the individual IPs of each pod. So here I have the pod name, pod IP, and the actual FQDN. So here it is giving some wrong responses sometimes in the Minikube cluster, but here as we said that each headless service when associated with the stateful set controller, so each pod will get a unique name. So if you deploy stateful set controller and the stateful set controller is named as www, each pod will have the host name like this, and when you have headless service in front of them, each one will get the unique identity in the form of the name of individual pod and the headless service name. So which means if I have to target individual pod, so here individual pod in the sense I cannot use the IP addresses because IP address will keep change, but I have the stable identities in the form of web0, web1. So let's see how do I use that. So for this what I'm going to do is I'm going to create an nginx pod, and I'm going to just target individual pod. So first we are going to use curl and the name of the normal service, which is nginx normal, and the incoming port is 80. So every time when I use, so you can see that there are varying responses. So even in case if I use the headless service name, the responses are going to be random because it is still load balancing in the form of DNS round robin load balancing. But I can target a single pod here. So how do I target a single pod? So all I have to do is I have to use the pod name of the stateful set followed by dot followed by the headless service name. So here if I use this, see here I am getting the responses from only a single pod, which is web 0, because I'm targeting that pod. So if I just make it to web 1 here, so I'm getting the web 1 response, which means I'm now targeting the second pod. So if I have to use the write, I'll use this, and if I wanted to read, I can use the headless service name or cluster IP service name, because both of them actually round robin the request. So this is how you work with stateful sets. So let's see the actual application, which is a to-do application which I have just written. So this is basically a Python based application, and it is containerized. So it internally, it connects to a MySQL database. The first thing is, how do we actually create that database with multiple replicas, and how do we replicate the data? So for replicating the data, so I'll show you why the replication is needed and all. So for this, I'm going to deploy a simple application. The first thing is, so under the Kubernetes, so I have multiple folders here. So in the Python to do app, I have inside Kubernetes, I have these 3 different folders, 00, 01 and 02, and I have a readme file at the outside, which will be used for this demo. So first thing which we'll do is we'll first deploy the application from 00 folder, which is MySQL deployment and application deployment. So here my application is stateless, but I'm making it stateful by saving the data in the MySQL. So we know that all the databases should use stateful sets, but let's see why we need it in the first place by just starting with deployments. The first thing is my application needs the database to be available. So first let's deploy the database first. Here I'm going to, as I already said, so as I already said, this is the application. As I already said, this is the application that I'm going to use. So here we have a simple to-do application, which will just write the to-do items to the database. So first what we'll do is we'll first create the MySQL deployment. So I have the MySQL deployment here, and the replicas I'm setting as 1. So that means every read and write operations will be taken by only one single instance, and the container image is MySQL 5.7, and the container port is 3306, which is MySQL port. And we all know that MySQL needs a root password to begin with. So what I did is, so I created a secret, and with the secret that is holding root password, which is base64 encoded of the name root. So this root password is itself root. So I'm mounting that secret as an environment variable. So MySQL root password becomes the root itself, which I am using in the form of secret. And the database name MySQL wants to connect is to-do. So here I'll make sure that this to-do database is already existing. So how do I make sure that this to-do database is always already existing? So for this, what I did is I created a config map, and the name of the config map file is init.sql, and the content of that init.sql is, so create database to-do if it doesn't exist, and use that database. So here I'm creating various columns. The column is having the to-do number, which is integer, and this is not null. It should not be null, and it should be auto incremented, and it should be set as primary key. So which means, so you don't have to write like you don't have to manually increase this to do number. It will be automatically incremented. And the title of the to do and whether it is completed or not, which is set as boolean. So this init SQL as a config map where exactly I'm mounting. So first I'm creating a volume with config map, and I'm taking this volume and I'm mounting it into this location where your MySQL will expect the init SQL file. So when it starts, actually it reads the contents of this file and then it will configure its database. Since I have created this init SQL file with creation of database and the table, so my table will be automatically created in this deployment. Okay, so I created a volume and I just mounted it. So this is about the MySQL deployment. So initially I'll start with one replica. So all the processes are mentioned in the readme file outside. So here the first thing which we'll do is we'll deploy MySQL, and after that we'll deploy the application. So let's see the application. Okay, so before that let's deploy the MySQL database first. So we have created everything. Now let's go to the application deployment. So here the application is again deployed through deployment controller, and this is the name of the image, this is the container port, and here as the database URI, because my Python application needs a database URL, I am supplying it as an environment variable within my application, and this environment variable actually connects to my database. So in case of database URI, which is a URL to connect to the database, I need to give the username :password at the rate of the actual IP or the DNS name of my database, followed by the port on which the database is listening on, / the database name itself. As I said, MySQL is exposed as the normal service here, so it is not exposed as the basically headless service, because I can just show the diagram once. Here I have the MySQL database and it is exposed to cluster IP. So the cluster IP name is MySQL. Okay, and the app deployment in the database URI. So root is the username of my database, and password is also root, which I set it as secret. And MySQL-normal is the name of the MySQL service. .default svc cluster.local is the fully qualified domain name. 3306 is the database name, database port, and to-do is the database name. So my Python application, once it comes up, it talks to this database. So make sure that your database is already running, and I'm exposing my Python application through a node port with a static value of 31,000. So let's apply this file, my deployment. Now let's get the number of pods and services. So here I have the MySQL pod, and my Python application has not come up yet. Okay, so let's see why my Python application has not come up. So this is MySQL. So if I just check the deployments, so MySQL is there. Okay, so we again applied the MySQL only, we did not apply the app deployment file. Okay, my deployment is now created. Let's just check the pods and services. So now my MySQL is also running, my pod is also running. My pod is exposed, the front end exposed as 31,000, and I get the IP address of my Minikube cluster by running Minikube IP, and this is the IP address of my Minikube cluster. So what I'll do is I'll just use the 31,000 as the node port, and so this is response from the host. Since I have only one front end pod, so that is responding it. So let's see what will happen if I write some data. So let's say I'll create some to-do entries like sending email, and then something like some random names and to-do items I'm entering. So these are the items that my Python has written to a database. Now let's see what will how do I check the data. So if I just check the pod, so there is only one replica of my MySQL. So only to this replica actually the write requests are going. Since I added three to-do items, so these three to-do items should be available in the database. So for this, what I'm going to do is first I'm going to create a MySQL client. So kubectl run MySQL client, image is this, and run. Then what we are going to do is we are going to connect to that MySQL. So let me explain this one a bit. So how do I connect my client is, so first create a client, and then as a first command, so what you have to do is you have to invoke the MySQL client utility, and you have to say where exactly the host is running. Since MySQL deployment is accessible through MySQL normal service with the user as root and password as root and to do as the database, I'm selecting everything from the to do table. So this is the complete request. So if you see, MySQL normal is the service, so I'm using the host as the service because internally that is the service. Okay, so this pod, so here instead of this pod, what I did is I created a MySQL client. So this is the client, so I'm asking the client to talk to this service. So this service name is just acting like the host on which your database is hosted. So this is the actual command to create a client. And also, one second, so this will just create a client and it will show you the data. So if you see here, I have the ID, title and complete status, everything. So if I just go back to the UI part, and if I mark one as completed, then if I just query the database, so my writing should be in the completion state. So here this is in the completion state. So this is fine because I only have one replica. So if I just get the number of pods, I have the only one replica. So my Python pod is using the MySQL normal as the service name, and then it is talking to the actual single instance. So what if I have multiple instances like this? So what if I use the same cluster IP name as the host? Let's see what will happen in this case. So what we will do is first we will scale this MySQL deployment to 3 replicas. So in case of deployments, you will see how the replicas are scaled. If you see, so all are scaled at the same time. So all the 2 replicas are created at the same time. So this way you will not be creating a much better replication algorithm, because if you go from 1 to 3 replicas, so if I have one MySQL replica and if I immediately created 2 at the same time, so both have to start from the individual both have to start replicating from the master instance. So this is the case of your deployment controller. But in case of stateful sets, right, so if I increase from 1 to 3, directly the scale up will not happen 1 to 3. So second replica will be created by replicating the data from the first instance, and the third replica will be created by replicating from the second instance. So this way you can avoid loading the first instance. So that is the first advantage here. Now since I have 3 pods here, let's see what will happen if I keep refreshing this page. Remember, refreshing this page indicates taking the data from the backend database, but this time there are 3 replicas and only first replica is holding your data. The rest all replicas doesn't have your data because we still haven't created any replication algorithm. So if this pod sends a request to this cluster IP, so it will load balance a request among all the backend instances. So let's see how this will happen. So let's click on refresh. Now this read request went to the some other database, some other replica inside that database which doesn't have that data. So if I refresh again, it is null. If I refresh third time, it is again giving the information, because this time the request is sent to the first instance which is actually having that data. So this is the actual disadvantage with this particular MySQL deployment without any replication, because you cannot target a single instance, because you cannot use the IP address, you cannot use the name of the pod, because both of them are ever changing. So this is the disadvantage of using. So if you want, you can also check the the database entries by creating the MySQL client, but talking to the normal service. So first time you got the response. See, second time you did not get any response because the read request went to the some other pod. Third time you got, this time luckily the request went to the first instance. So this time again it's a failure. So these are the disadvantages. So what we'll do, let's delete everything from this folder. Now let's go to the second example. So in the second example, what we did is we created a MySQL stateful set here. So I have a MySQL stateful set which we already seen. So we have the headless service and the normal service, and I have a config map that will just create the init script. I have the stateful set with the service name as the headless service, so which means every pod in this stateful set gets a unique identity. That is, if the stateful set name is MySQL, so every pod will be MySQL 0, MySQL 1, MySQL 2, etc. And I used that volume mounts. Here I did not use any volume claim templates because if you want, you can also use volume claim templates. The only thing which I'm not doing here is I'm not using any PVCs for individual pods, because this is just a demo, but in the real case scenarios you should use the PVCs. Okay, so this is the stateful set with only one replica. So what I'm going to do is I'm just going to deploy this stateful set of MySQL deployment. So just run kubectl guest STS and everything is in running state. So pod and SVC. So you have the two services here. One is the normal service, one is the headless service. So we are going to implement the second thing here. So in case if I want to just write it to only one instance here. So here I wanted to only target primary instance. Okay. So for this I need to use the headless service. Headless service, when combined with the name of the individual parts of the stateful set, gives a unique identification. But when in case of reading, what I'll do is I'll use the cluster IP service. So for this, what I'm going to do, since I already have headless service and normal service both created for this database, so I'm going to deploy this app deployment. Here this deployment is for your Python application with a simple node port, which we already seen. Here the database URI is also same. So here I'm just talking to the MySQL normal, so which means the data is sent to the normal service. But here when you talk to the normal service, all the the requests are load balanced, but fortunately we only have one instance, so that will take the both read and write operations. Okay, so everything is mentioned in the documentation here. So first stateful sets are deployed. Now let's deploy the application file. So it's kubectl apply app deployment.yaml. So we have just deployed our application and it can be accessed on 31,000. Okay, so what we'll do, so we'll access the application on 31,000. You can see I'm able to access this application here. So here as the database URI in the app deployment, I use the normal service. So which means, so if I have a Python pod here and I only have one MySQL instance under the stateful set controller, and through normal service I'm accessing it. So what will happen if I use the headless service in this case, because I also use the headless service, so it doesn't make any sense. So all the steps are already given here. Okay, so what I can do is I can use the headless service here. So headless service name is MySQL headless. So even though if you change it to headless service and redeploy, so the deployment got configured, but since I only have one instance here in the MySQL stateful set, using headless service or normal service doesn't matter, because both of them are going to redirect the request to the same backend pod. So you can also refresh your page and see it is still the same thing. So only thing is pod got restarted, I mean it got upgraded with a new pod hash. So same thing. So I'm using the stateful set. So what if I increase the number of replicas in this case? So instead of using one replica in the stateful set, so what I'm going to use, I'm going to increase the stateful set called MySQL with 3 replicas. So once if I increase, so you can see that, so both, I mean everything will start in the order. So you can see both of them did not start at the same time. So first MySQL 1 has started and then MySQL 2 has started. And remember here I have not created any data replication here. So MySQL 1 will start and after that 2 will start, but here 1 won't replicate from 0 and 2 won't replicate from 1 because there is no replication algorithm yet. Replication algorithm is not inbuilt into stateful set. Stateful set provides a unique identity, so using which your data replication becomes much easier, but it doesn't mean that stateful set has the replication algorithm. So now since my if you see the app deployment, my requests are getting forwarded to the headless service, and headless service basically can also rewrite the request, rewrite the request to all the backend instances in the load balancing fashion. So what I'm going to do is I'm going to first add some element, first to do element called some test. So added this test to do element, but why exactly this is not added? Because what happened is when I use headless service, it is load balancing. So when I added the first entry, it went into some replica, but when I try to read it back to show you on the screen, it read from the different one. Because there is no data replication, all the read writes are inconsistent. So you can refresh, so somewhere you will see the test. See here test is available. Let's say I'm going to use test2. So I entered here, the test2 is got saved into some other instance. When I read it back, so only test1 is available in one instance, test2 is available in another instance, and third instance may not have anything at all. See here, these are inconsistent because all I did is my Python application is using this headless service for both read and write access, but here I have multiple MySQL instances, so all the read writes will be inconsistent because I'm using the headless service, which is actually working like your normal service. So how do I fix this? So before fixing it, let's log in into each database and let's see how to read the data from each one. So here I'm creating the MySQL client, and as the MySQL host, where exactly host is running, I'm actually sending it to headless. Okay, so I'm actually sending the request to headless, and I'm going to see each responses. So I'm going to get different responses because headless will obviously load balance. See, one database has a test2, and maybe some one will have test1. Let's see this has test1. So one doesn't have anything at all, so one has empty. So there is no data replication and there is no data consistency. But how do I see individual pods? So we know that each part of the MySQL stateful set has a unique identity, which is called MySQL 0 or MySQL 1 and 2. So if I have to target individual pods, okay, so what I can do is I can use the fully qualified domain name. So as I already said, if this is the name of the pod MySQL 0 and this is 0, this is 1 and this is 2, I can directly ask my client or any pod to directly talk to this particular first instance by using the name followed by the headless service. So I'm going to do the same thing. So here when I'm trying to create a client, I'm asking the client called MySQL client to talk to a pod known as MySQL -0.headless. So this gives unique identity to that the first pod of your MySQL stateful set in the form of pod name .headless service. I'm asking it to directly talk to this pod using this FQDN. See, this is directly talking to the first instance, and every time I'm getting the same response because I am targeting that pod. So what if I wanted to see what exactly are available in the first replica? So this is the culprit. So this doesn't have any data at all. So what if I have to check the other one? So it is MySQL -2. So this is how you can check individual datas. Now what I'm going to do is, since I know that through headless service I can actually write the data every time. So what I'll do is, so for writing I'll use this application, okay, on 31,000. Okay, so this application will only write the data. Of course it can read, but in the database URI, what I'm doing is I am asking it to always talk to MySQL -0, which is the first one, and dot the headless service name, and I'm going to just run the same file again. So this will get updated. Okay, so this is the only URI, which means this particular to-do application will always contact the MySQL -0 irrespective of the number of replicas. So now if I just show this example, okay, so if I refresh n number of times, the request will always go to the first one. Even if I write something, let's say if I write my name or if I write something, these writes are happening only to the first instance, okay, because that is the same URL I am using. So what if I create another application that will just talk to MySQL normal as a service to just act like a reader? So for this I have one more YAML file which is just acting like a reader, and this application is listening on 32,000. It's the same Python to do application which I've just created, but the database URI, it is now pointing to the MySQL normal. Okay, so this one I wanted to use it as read operations. Okay, so I'm going to run the same. So this particular application will always talk to the MySQL normal service. In case of MySQL normal service, we know that any request that is sent, it will always be load balanced. So in this case, since it is load balancing, it is going to get the inconsistent responses, because only first one has this test Vikram and DevOps, and if you talk about the other ones do not have them at all. So this is for the writing. So this particular API call can be used for writing, which means I can use this particular URL for reading. For writing, I can target a single pod like this, but since there is no data replication across all of them, so I'm getting the inconsistent read operations, which we are going to fix in some time. So let's delete everything from this. So how do I create the replication and to work with the replication? So actually your Kubernetes also has an important example on how to replicate the databases. So you can also search for MySQL replicated Kubernetes. So there is an example basically. So run a replicated stateful set application, where they'll show you how to create a MySQL and how to create the replication algorithm and all, which means whenever a pod starts, okay, so in case of MySQL with let's say I have 4 different let's say I have one replica which is already running, okay, which has some 10 user accounts information. Now if I have to scale it to 5, what will happen is, so second instance will start. At the time of starting, it will replicate the data from the first instance. A third replica will start by replicating data from second. So this way the replication will work, and at the same time your scaling will also happen. So but this replication algorithm is not by default it comes with stateful set. You need to create it. So in case if you are directly creating a stateful set with 5 replicas, so usually first will start and it won't replicate from anything, because this is the first master one. Now second one will start replicating from 1, third will start replicating from 2, like that. So this is how the replication algorithm works, and this is perfectly explained it here, but I'm not going to use the one which is given here. So what I'm going to do is I'm going to basically use a Helm chart, and that Helm chart already has that replication algorithm. So what you have to do is you have to add this Helm repository and then pull this Bitnami MySQL Helm chart. So I'm going to go to artifacthub.io. So if you already know how to download the Helm charts, it's basically artifacthub.io, and you can search for MySQL Helm chart by Bitnami. So this one is MySQL by Bitnami. So you'll have the commands to add the repository and then install, but before installing I wanted to make some changes, so that's the reason why. So I wanted to add the repository, and I wanted to update the repository index locally. And instead of installing this Bitnami MySQL, first what I'm going to do is I'm going to pull the Helm chart, which will be pulled in the tar file. But instead of extracting after pulling, I'm just passing --untar so that this will be automatically pulled. So what I'm going to do is I'm going to pull it somewhere in my downloads folder so that it will be easy for me. So I'm pulling it in my downloads folder, and automatically, okay, so it says it is already existing. So let me delete it and pull it again. Since it will be automatically extracted, so I'll get as a folder. So I'll use code and MySQL. So automatically in the VS Code this gets open, or if you know any of the code editors, you can open it. So automatically it opens as the extracted one. So I can go to values.yaml file and I can make some changes here. The first change which I'm going to do is I'm going to basically set it in the replication mode. So here I can have the replication mode set by just changing from standalone to the replication. So I have to make this as replication so that I can have multiple replicas and each of them will replicate among themselves. And here as the database, so there are a lot of changes you need to do. So you need to create the to-do database and all. Okay, so everything I already collected and I've given it in the files itself directly in the repository. So if you go to this second example and if you open the MySQL chart and open the values.yaml file, so everything is already given here. So what are the changes I basically did is so let me show from beginning. The first thing which I did is adding the replication mode. So the architecture is set as replication, so depending upon the number of instances that you deploy, replication will take place. And the root password is set as root, and the database I am setting as to do. So automatically when it is authenticating, so the root password it will use as root and it will connect to the to do database, and replication password you can use as replicator. And this is a custom initdb script which I have to use because I need to actually connect to the MySQL database, and I have to create the to-do database and then create a to-do table in it. So I'm creating a shell script which will automatically connect it to the local host. So here if you see, I have not used -h and localhost because this MySQL client will automatically connect to the same server, and the port is 3306, user is root, password is root, and to-do is the database. And I'm asking it to just run this script. So create database to do and use the table and create ID, title, and complete as the structure. So it's just a DB structure here. And apart from that, what you have to do is you have to also use the storage class name. So in case if you are using in Kubernetes, so default storage class will be selected. So otherwise your storage class has to be mentioned. And also here the storage class, if you don't mention, it will automatically take. The sizes I'm reducing it to only 100 MB because I don't have so much of storage in Minikube. So make sure that you change the storage of the master database as well as the replicated database. So here for the secondary databases also, you can set how many secondary instances you need for the read operations. And you can also set the individual PVC size by setting the proper PVC size here. So here 100 MB is the storage I wanted to use for both master and the secondary databases. And if you want to change the resources and all, you can also change it. So this is about the MySQL chart. So what I'm going to do is I'm going to first install this MySQL chart by using helm install MySQL and the folder. So where exactly is your folder? It is under 02. So let's switch the folder to 02 and let's release this MySQL chart. So here once you install this MySQL chart, right, so here MySQL will also show you the primary database URL and the secondary database URL. So it is just saying, so if you want to connect to a primary database for both read and write operations, all you have to do is you have to use MySQL primary dot default as the host name. So they are directly saying, so you can target your write operation, okay, by just using this one. Or if you want to read from all the instances, what you have to do is you have to use MySQL hyphen secondary. So here they have internally created the services in such a way that so they are directly giving the endpoints to read and write by only one instance and read from all the available. So you can just verify it by getting all the stateful sets. So here you'll have the two stateful sets. One is the primary, which takes the write operations. One is the secondary, which is taking both read and write operations. Read operations. So your write will be here, read will be from everywhere. So when MySQL secondary comes up, okay, you can also get the pods. So they'll try to replicate from the primary. So first primary will come, secondary 0 will come up, because this is belonging to one stateful set and the first one belong to the other stateful set. Okay, so this is how you deploy the MySQL chart, but this is not the end. So since we deploy the chart, let's first deploy the application as well. So inside the application deployment, so as you know that the deployment file, I'm using it for the write operation. So as they already said, in order to use the write, I need to use this. So I'm using this endpoint to write. Okay, so I'm going to just apply this file, which will just take it as take it for the write operations. So MySQL, so where exactly these are available? So okay, sorry, it's app deployment .yaml file. Since this is the endpoint for the just the write operations, and this is exposed on 31,000. So let's see whether 31,000 will be available or not. Okay, so this is 31,000. If you see, so already we created PVCs before. So what we are going to do now is let's uninstall everything and let's start from scratch. So for this, first I'll uninstall the Helm release, Helm uninstall MySQL, and I'm also going to delete this app deployment. And since this cluster has lot of PV and PVCs already available, so I'm deleting everything. So kindly do not do this in production environment. Since this is my local environment, I am deleting all PV and PVCs in my local Minikube cluster. Now I'll release the MySQL chart again, and let's wait till all the instances are up. So you can see primary came up, and secondaries are they will come up sometime. Okay, see MySQL 0 come, and secondary 1 is starting. It starts once secondary 0 is up and running. So let's wait when every pod comes up. So last one is also in the running state. So now what we'll do is we are going to deploy the application file. So it is kubectl apply -f, and the name of the file application deployment. So where I'm using the only the write endpoint. So if you directly use this particular port number, this is always going to okay. So why this is, let's see the PVCs, because these are retaining the data. So PVC is all started right now. Okay, so let's see. Let's maybe these are from the cache, so let's open it in the incognito. 31,000. Okay, still these are there. Okay, so what I'm going to do is I'm going to delete them. So this is the reader endpoint. Now what I'm write endpoint. Now whatever I'm going to write, so you can see it gets written here. Now what I'm going to do is I'm going to also create another application for reading. So this is the reader application where MySQL normal. So this is not MySQL normal because for both read operations, so it is asking us to use MySQL secondary. So it is here, MySQL secondary. Yeah, so it is already there. So now I'm creating another application called reader, which is actually using the endpoint of the reader. So using this application on port 32,000, so I can actually read the data, and it will be read from all the available instances. So if I use 32,000 here, this will be read from all the instances. Even if you refresh hundreds of times, so you can see basically this is getting from the other instances because the PVCs are not deleted properly. So now I have deleted everything. So what I'm going to do now is I'm going to release the same Helm chart. So this time you can also use a separate and a release name also. Okay, so I'm going to use MySQL demo as the release name. So here your endpoint will also change. So this is the endpoint that they're asking us to use for both read and write, but only for read operation they're asking us to use the secondary. So for secondary, for read operations you can use the secondary's cluster IP service, but for writing I can use this primary one. Since all these are now in the deployment state, so I should wait before everything comes up so that my database or my application can connect to. So let's wait when till all primary and secondary database comes online. So now all the containers are in the running state. So now as they already said, so in order for the write operations, I can use this as the endpoint. So I'm going to do the same thing here. So I'm going to take this URL. So I'm going to use this app deployment and change the URL for my write operations. So this is the write operations container or the pod which is listening on 31,000. So I'm going to apply this file. So this will just service as my application that is just writing. Okay, so this is just the write API, and I'm going to use this application on 31,000, but this is just the demo so that I'm using the same application on two different ports with two different URLs like this. But in your actual application, to write some data you need to use this URL. To read the data you should use the secondary instead of primary, because in the Helm chart they have clearly mentioned. Or else you can use the combination of headless services and the cluster IP services to manage the read and write operations. So let's see this one in 31,000. So if you see I'm able to only connect to the write endpoint or the write database. So I'll use test in one, and let's create some to-do items. So here in this 31,000 the application is actually connecting to only one database, that is only it is connected to the write database, which is the first instance of the primary. But in case of read, so how do I read the data? Since I cannot dynamically change it here, so I created one more pod which will be listen on 32,000 here. So instead of write, I'll be using the read API. So here in the read API, so they gave this as the name. So all I'm going to use is I'm going to change the host name. So this will point to the secondary service, cluster IP service to be specific. So I'm just going to save this file, and let's apply this file again. So this is the reader part. Since reader is now listening on 32,000, what I can do is I can visit 32,000. Now you can see all the replications are working. So if I add something, to the right instance, that is the first instance. So every instance will get replicated. So if you refresh here, which is actually reading from all the instances, you are getting the similar responses. But how do I test it from the database point of view? So for this, what I'm going to do is I'm going to connect to a individual database. Okay, so first is I'm going to connect to the primary database. So I'm going to use this here. This is the primary database. So inside the primary database, as I mentioned, so we should use the MySQL hyphen demo hyphen primary for connecting to the primary. So I'm going to use the same. So demo hyphen primary. So I'm going to see the entire list here. So if I have to connect to the individual instances of the if I have to connect to the read endpoint, so instead of primary, I should give secondary here. So I'm now connecting to the secondary instance here. So in the second instance also, every read operation will be consistent because replication has already happened. But let's see whether the replication is actually working or not by checking the last instance in my secondary stateful set. So if I just get the number of pods in the stateful set of secondary, so this one is the name. So I'm going to connect only to the second instance by using the headless service name followed by the pod name. Sorry, the pod name dot the actual headless service name. So this will make sure that I always connect to the last instance for the read operation. So I'm reading the data from the last here. So MySQL hyphen 2 indicates the last. So you can verify whether it is last or not, okay, by putting as 3. So in this case 3 pod is not, it won't be there. Okay, so here the client itself is that unknown MySQL server host, because the third is not available, only till 2 is there. So what I'm going to do is from the UI, okay, from the right endpoint on 32,001, what I'm going to do is I'm going to write some data. So here I'm writing dummy as the text in the primary instance. So as I write this data to primary instance, all the secondary should actually replicate it. So I'll just write it from the UI. At the same time, immediately I'll check it in the last instance. So the last database instance of the secondary replication database. So let's see this demo. So let's add it and immediately just check the secondary one. See here, dummy 000 is added to the last. So that means replication is working. So you can also check the zeroth of the the secondary stateful set, or you can also connect to the second instance of the database, or in fact you can also connect to the primary one, so which with the name MySQL demo primary. So even to this endpoint your read operations will perfectly work. So I think so this is not the endpoint, right? So MySQL demo primary is the service name, so you should not have another service name in the name. Okay, so I'm connecting to the primary database, so the primary cluster IP service. Now if I again check the last instance, that is MySQL 2, anyways this dummy is available. So what I'm going to do is I'm going to quickly delete everything here. And then immediately check in the final secondary database. So the entire data should be gone, so which means your complete replication is working. So whatever you write to the primary through primary endpoint, the secondary instances will replicate from the primary endpoint, and for write operations you use primary endpoint. For all the read operations you can use a secondary endpoint, which is given specifically to this Helm chart. But ideally if you are setting everything up manually, so what you have to do is, if I have one Python application, any application, and if I have multiple instances of MySQL stateful set, and the first one, if it is named as MySQL hyphen 0, and this is named as MySQL hyphen 1, and if this is named as MySQL hyphen 2, so what you can do is you can create a headless service. Let's say the name of the headless service is MySQL underscore h. Let's assume. Now if your Python application will talk to this, it will always load balance. But if I have to write only to this one here from your Python application, what you have to do is you have to use the pod name, which is MySQL-0 dot followed by the headless service name, which is MySQL-_h. So this endpoint will talk to will directly connect you to the first pod. But if you want to read, so what you can do is you can simply use MySQL_h. So this headless service, when it receives a request, it will automatically load balance it across all the available pods. So this is the actually difference between your deployment and stateful set, and this is the reason why we actually use stateful sets for all the stateful applications such as deployments.